So yes, I'm Andrew Reed, and on behalf of my co-authors, Pranay, Jain, and Mike Reiter, welcome to this talk on our work, Near Optimal Constrained Padding for Object Retrievals with Dependencies. So what is the setting? So the setting here is that you've got a client that is retrieving objects from a trusted object store. Those objects could have different sizes, and then they also could have dependencies between their retrievals that then lend themselves to different sequences of retrievals. These objects, though, are assumed to be encrypted. Now, the adversary in this setting is a network observer that is observing the objects as they are being retrieved, and it is using its knowledge of the objects that are on the object store to potentially try to identify which objects were retrieved. So in words, this threat is the network observer that is able to discern the object sizes of sequentially retrieved objects, and its goal is to identify which objects were retrieved. We assume that it basically knows everything about the object store, knows the object sizes, knows what possible sequences there are, also knows the distribution perhaps on those sequences, and then also knows the padding defense that the object store is employing. So then the trusted object store's goal is this. It wants a padding scheme that can best thwart this adversary, but one that controls the per object overhead, padding overhead applied to every single object. Now, one thing to note here is that this object store is only willing to pad objects. It's not going to insert dummy decoy objects into the stream. It's only going to apply padding onto the objects that were requested. So what is our solution here? Our approach is to minimize this metric known as the Simpson mutual information of order infinity. For the remainder of this talk, I'll just refer to it as I infinity. Some of you may know it from the literature. It's also referred to as min capacity or maximal leakage. So we want to minimize I infinity between the sequence of object padded sizes and their identities. But with this constraint, that no single object is padded by more than a maximum pad factor, which we refer to as C target, and then every object is served in full. Now, note here that because of this C target, this maximum padding factor, it's possible for some objects to remain isolated in that if there's no other object to which they could be padded because of this constraint, then they would just be outed by their size when retrieved. Before I move on, why did we choose this metric? Well, there's two really great properties that I infinity gives us, as mentioned in these references here. One is that it upper bounds mutual information across all distributions on the sequences, S. And then also another way to look at it is the adversary gains information when it sees these sequences of object padded sizes. I infinity serves as an upper bound on that gain, again, across all distributions on S. So then our algorithm, just simply put, it's a linear program that we named padding for sequences. We refer to it as PFS. It takes as input the set of objects and the set of possible sequences. Now, I want to make sure I clarify this. I've mentioned previously the distributions. All that is required for the linear program is just what objects are on the object store and what are the possible sequences. The linear program does not require the distributions. And then also it takes as input that maximum pad factor of C target. And then it outputs a padding scheme that minimizes an upper bound on I infinity, and it does not violate C target for any of the objects on the object store. Also, this padding scheme is memoryless. And by that we mean that the object store does not need to remember what objects have already been retrieved, previously retrieved by the client. It just looks at each request anew, consults the padding scheme, adds the padding, ships it off to the client. So as part of our evaluation on our algorithm, PFS, we selected 3 competitors from the literature. We chose these competitors because, one, they each target a different privacy metric. Also, they each operate differently. BDK and MVMD from the literature, they both were designed to target sequences, as does PFS. PWAD, on the other hand, was designed to target independent object retrievals. A similarity, though, with PWAD is that it does also take ctarget as an input, and then it also minimizes I-infinity, but again, it does so for independent object retrievals. And before I move on, I just want to touch on the inputs that are required for each of the algorithms. When we look at the algorithms that are focused on sequences, again, BDK, MVMD, and ours, PFS. PFS requires the least amount of inputs required to run the algorithm. We also created 3 data sets in our paper for evaluation, but in the interest of time for the presentation, I'll just focus on one of the data sets that we created, which is our autocomplete data set. So this data set models, imagine a user typing in a search term at the Google search prompt. As that user types each character, an updated list of potential suggested search terms are returned to the user by Google. And so those suggested search terms then become the objects that are being retrieved by the client as the client types each character, and they can vary in size. So for instance, for the word tree, if a user were to type that in our data set, it would have wound up with the 4 sizes being returned by Google in the bottom. This data set has just shy of 900 full words for a total of a little under 4,000 total sequences. So now for our evaluation, I will first orient you to this slide because again, I can tell there's a lot going on here. So a little bit of orientation here before we get into the results here. So on this slide on the left hand, this chart is charting for each of the algorithms the I-infinity that was the result of running that algorithm for increasing sequence lengths. So at each sequence length, for increasing sequence length, we run the algorithm, the different padding algorithms, and then we chart what I-infinity resulted from running the padding scheme. And we chart them at each sequence length. One thing to note about how we calculate this metric is, let's say, for instance, at sequence length 3, if a word was only 1 or 2 characters long, then it's no longer in consideration because now the adversary knows that the word could not be one of those sequence lengths. But at sequence length 3, for example, we do also include in the metric the prefixes of all sequences that are 3 or longer, and we truncate them at sequence length 3. But now I also need to explain for PWAD and PFS, which take ctarget as an input, we ran them with increasing values for ctarget. So now I'll do a breakdown for what that looks like just for PFS. So what I've highlighted here in green is this is PFS when run with a ctarget of C1.05, so it's only willing to pad an additional 5% on each of the objects. So in that case, the green bar extends all the way to the top of the bar. As you increase ctarget, as you increase the amount that you are willing to pad your objects, I-infinity decreases. In this chart, lower is better. You want to minimize I-infinity. Lower I-infinity means more privacy. Now, also, beginning with C1.25, let me go now to the chart on the right. The chart on the right is plotting the padding factors that result from these algorithms. So the way we construct the chart on the right is we ran each of the algorithms, took its padding scheme that the algorithm returned, and then applied that padding scheme to all of the objects on the data store. On the x-axis, what we report is the maximum pad factor. So after you apply the padding scheme to all of the objects, what was the largest pad factor that was applied to any one of the objects? That then becomes C max. but then we also plot on the y-axis what was the average resultant pad factor after applying the padding scheme to all of the objects. For this chart, values in the lower left are going to be better because that indicates that less padding was applied to the objects, whether maximum or average. So now starting with C1.25 for PFS, plotting that as a green circle. Again, now advancing both charts at the same time, C1.5, I infinity goes down, the padding goes up, and then down to C2.0. So now that I've oriented everyone to the way the chart works, let me now kind of freeze on one of the values for C target here, 1.25 specifically, and now highlighted at the top of each one of those bars where that value, the resultant value, lies. So now we see here that PFS in green, you can see that it's clearly beating one of our competitors' BDK kind of across all the sequence lengths. Beats quite handily NVMD for most of the lower sequence lengths. There's 2 sequence lengths here at 7 and 8 where NVMD just barely edges out, but then PFS starts to win. And then also PFS beats PWAD once you get past the first couple sequence lengths. And then on the right, we see that it does this with very little padding overhead compared to especially NVMD and BDK, which do not take C target as an input. So now, for the purposes of this talk, just focused on one of our evaluations and one of our data sets. Also available in the paper, we compare PFS against BDK and NVMD using their metrics. We have 2 additional data sets that we used for evaluation. We also conducted precision recall tests that model a network adversary trying to guess a subset of the sequences. And then we also present a faster alternative to PFS named padding for graphs. We also make our source code and data sets available at the link provided. Thank you. What are your questions?